So question 1 reads, calculate the level of stress in each section of the bar in the given diagram if it's strained by a tensile force of 20 kilonewtons. Okay, so that will be axial to the axis of the component. Question 1b, determine the total change in length. So the total extension experienced by the bar, so step bar there. And we're also being tasked in question C to work out the average factor of safety of the step bar if the yield limit is given at 205 MPa. Alright, so how do we go about solving this problem? So if you want to have a go based on the letter that you know, feel free to do so. So these are the answers that we are expected to achieve after working through this problem. So the simplest way of going about doing this problem is to break the component into two segments. So let's call this section A or section 1. So section A or section 1, we're assuming that there is an internal force or internal reaction that will cause the component to be in a state of equilibrium. So both ends will experience a magnitude of force of 20 kilonewtons, but the sensors will be in opposite directions to keep the body in a state of equilibrium. Okay, so for section 1, the diameter is 50 millimeters and the length of that section of the step bar is 80 millimeters. And we do likewise for section 2 or section B, if you want to call it that. So again, it's also experiencing a tensile load of 20 kilonewtons. But this is more of a hollow tube. So you've got an internal bore or internal hole that goes all the way through that particular section, and that measures at 10 millimeters in diameter, and the outside diameter is 25 millimeters, and the span of that particular section is 60 millimeters. So let's have a go working this out, and I'll come back to go through the summary for this particular problem. Let's go through this problem. So this is a diagram of the step bar that we have. So we've got two sections. So let's call this part section 1, and let's call the hollow part section 2. So what we're going to do is we're going to figure out what the stress is for section 1. Use that information to help us find out what the stress is in section 2. And once we figure out what the stresses are, we can then proceed to calculate what the elongation is for each section, and then add the two to get the total extension experienced by the component when subjected to a force of 20 kilonewtons. So we first off calculate the area. So area of section 1. So the diameter, so let's say D1, is given as 50 millimeters. Therefore the area, A1, will be equal to pi over 4 times D1 squared. And that will be equal to pi over 4 times into bracket 50 squared. Let's bring our handy calculator. So we have pi over 4 times 50 squared. Now I'm very certain that some of you may ask, why not convert it from millimeters to meters? It's up to you. You can do it either way. You just need to be very careful when it comes to calculating the stress. Alright? So when you calculate the stress, you need to make sure that any measurement in the basis of meters stays in meters. Alright? Okay, so that gives us 1963 let's do this 5 millimeters squared. We know that the force is 20 kilonewtons, so we can then calculate the stress in section 1, and that would be sigma 1 is equal to F over A1. It's fairly straightforward stuff. So this means 20,000. Okay, so kilos 1,000 divided by 1963.5. 20,000 divided by 1963.5, and that gives about 10.19 Newton per millimeter squared, which is the same as 10.19 MPa. Okay, so don't forget, Newton per millimeter squared is the same as megapascal. So we've done that part. So we can now calculate the area of section 2. Now we shouldn't forget that this is a hollow section. So the area A2 will be equal to area with respect to the outer diameter minus the area with respect to the hollow. Alright? We know about the area of a circle, so again, as I stated, if you want to use pi r squared, it's up to you, is equal to pi over 4 d squared. Okay? So we shouldn't forget that. So in terms of the hollow section, that will be A0 is equal to pi over 4 times d0 squared. And the area with respect to the hollow section will be pi over 4 times dh squared. Alright. So d0 is equal to the outer diameter, and dh is equal to the inner or the hollow diameter. Okay. So what we're going to do is, since A2 is equal to A0 minus AH, if we substitute what these are, then this becomes pi over 4 d0 squared minus pi over 4 dh squared. So if we factorize pi over 4, we get pi over 4 into bracket d0 squared minus dh squared. And that defines A2. So we know that d0 from the problem is given as 25 millimeters. dh is given as 10 millimeters. So if we substitute these into our formula, A2 is equal to pi over 4 into bracket 25 squared minus 10 squared. So if you do the computation, 25 squared minus 10 squared, that will give pi over 4 times 525. So multiply that by pi over 4. And that would give 412.33 millimeters squared. So we've calculated A1 and A2. So from our equations for compatibility, since the force in section 1 is equal to the force in section 2, since this is the case, then sigma 1 times A1 should be equal to sigma 2 times A2. Okay, so we didn't forget that stress is equal to F over A. So making F the subject of this relationship, F is equal to sigma times A. So the product of the stress and its cross-sectional area. We know sigma 1, we calculated that. We know A1, we know A2. So if we make sigma 2 the subject of this equation, this will give us sigma 1 times the ratio of area 1 to area 2. So let's call that equation 2. So we can use this relationship to calculate the stress in the hollowed section of the step bar. So stress in hollowed section, so that will be section 2. So that is sigma 2 will be equal to 10.19 times into bracket area 1, which was 1963.5 divided by 412.33. So if you do the computation, what do we have? So we've got 1963.5 divided by 412.33. So that will leave 0.19 times 4.762. 10.19 times 4.762, and that would give about 48.52 Newton per millimeter squared, which is the same as 48.52 MPa. Okay, so we're back. So let's have a look at the problem in the very quick summary. So as we more or less stated, the tensile force in section 1 is equal to the tensile force in section 2. So that will be 20 kilonewtons. So F is equal to F1. So F1 is basically the force in section 1, which is equal to the force in section 2. So since stress is equal to F divided by A, we can then use it to come up with an expression in terms of solving this particular problem. So since F1 is equal to F2, and we know that from the fundamental stress equation, if we're going to make F the subject, that would be sigma times A, then sigma times A for section 1 will be equal to sigma times A for section 2. So using this relationship, what we can do is we can work out the area in one component, work out the area in the second section, work out the stress in one section, and what we do is for the unknown stress, we can just make that the subject of the equation to solve for the stress in either section A, section 1 or section 2. So similarly, we're still going to be using the engineer's formula, so hopefully by now you've gotten used to me using this particular formula. But again, if you want to use pi r squared, feel free to do so. So to work out the sectional area for section 1, A1 is equal to pi d1 squared divided by 4. So since d1 is equal to 50, we just introduce that into the equation and we get a result of 1963.5 millimeters squared. If you want to calculate in the basis of meters, feel free to do so. Since we know what the force is and we calculated this cross-sectional area, we can then proceed to calculate the stress in section 1. So sigma 1 is equal to F divided by A1. F is equal to 20 kilonewtons, which is 20 times 10 times 1,000, or 20,000 newtons, divided by 1,963, or if you want to say 1963.5, feel free to do so. We do the computation and we get 10.19 MPa. Okay, or if you want to express it as 10.2, feel free to do so. So we've worked out the stress and the area for one section. We could then use the same methodology to calculate for section 2 and use the compatibility equation to work out what the stress is. Now this is where we need to be very careful. Okay, so to work out the cross section, we have to work out the area of for respect to the outer diameter and deduct it from the area of the bore. And we deduct because you're removing material, so it can't quite make sense. So A2 is equal to pi over 4 into bracket D2 squared. So D2 is represented the outside diameter, okay, minus DH squared. So DH is representing the diameter of the hollow. So the diameter externally is 25. The diameter of the hollow or the bore is 10. You do the computation and you get 412.3 millimeters. So since sigma times A1 is equal to sigma times A2, to calculate for A2, sigma 2 will be equal to, or the stress in section 2 will be equal to sigma 1 times A1 divided by A2. And that's what's been done here. We've calculated sigma 1 of the stress in section 1 to be 10.19 times the ratio of area 1 to area 2, so that is 1963.5 divided by 412.3, and that leaves a value of 48.51 MPa. So we've worked out the first part of the question. So the next part is to calculate the extension. So the total extension will be delta LT. Alright? So the total extension experienced in the step bar, so going at delta LT will be equal to extension in section 1. So let's call that L1 plus delta L2. Alright? So that's the stated, this is the extension in section 1, and this would be the extension in section 2. So from first principle, based on what we've discussed to date, strain epsilon is equal to delta L, so the change in length or the extension divided by the original length. Okay, let's call that 3. So if we make delta L the subject, then delta L will be equal to the product of the strain and the original length. Okay, so let's call that 4. We also know that we can calculate the strain with respect to the Young's modulus and the stress. So since strain is also equal to the ratio of the stress to the modulus of resilience, what we can do is we can substitute this variable. So let's call this phi. we can substitute 5 so let's call that equation 5 and 4. So if we do so, we'll have delta L is equal to sigma over E, so let's say with respect to I, times the original length. Okay. So let's relate this expression to our problem. So the extension in section 1, which would be delta L1, will be equal to the stress divided by the Young's modulus with respect to section 1 times L1, and L1 is representative of the original length of section 1. Alright, so fairly straightforward. We know what the stress is. We've been given the elastic modulus, so E in the problem has been given to be 202 GPa. We calculated the stress to be 10.19 MPa, and the original length of section 1, that was given as 80 millimeters. Okay, now I want to work in the basis of 80 millimeters, so what I'm going to do is that is the same as 10.9 Newton per millimeter squared, and GPa in terms of millimeters will read 202 kilonewton per millimeter squared. So more or less the same thing. So I want to get my answer directly into millimeters. But again, as I stated, if you are unsure, then make sure that you keep your work in the basis of meters. Alright, just to be on the safe side. Then once you've done that, you can then convert it from meters into millimeters. Alright, so delta L1 will be equal to 10.19 divided by 202 times 10 to the power 3 multiplied by 80. So if we do the computation, what will we get? So 10.19 divided by 202 to the power 3, brackets closed, times 80. And that gives 4.0356 times 10 to the power minus 3 millimeters. So that's the extension experienced in section 1. So we'll do likewise for section 2. So extension in section 2. So delta L2 will be equal to sigma 2 over E times L2. Okay. So again, E is more or less the same as the previous, so that's 202 GPa. The stress, we calculated that to be 48.52 MPa. And L2 from the problem was given as 60 millimeters. So therefore, delta L2 is equal to 48.52 divided by 202 times 10 to the power of 3, bracket closed, times 60. Bring our handy calculator. So 48.52 divided by 202 times 10 to the 3, bracket close, times 60. And this gives 0.0144 millimeters. Therefore, the total extension delta LT will be equal to 4.0356 times 10 to the power minus 3 plus 0.0144. So just add 4.0356 exponent minus 3, and that would give 0.01845 millimeters. Or if you want to write this as 0.0185 millimeters, and that gives this total extension. So we've seen how the concept of the compatibility equations makes it easy for us to solve problems similar to this. So we're now going to calculate the extension. So how do we go about doing that? We know that stress is equal to force divided by area. Strain, which is characterized by epsilon, is equal to the change in length to the length. So if we want to calculate the extension, we make delta L the subject of the expression. Thus, delta L is equal to epsilon times L1. So how do we go about calculating the strain? Well, we know that the strain from first principles is equal to the ratio of the stress to the Young's modulus. So once we calculate the strain, we can then calculate for the extension in section 1. So for section 1, we calculated the stress to be 10.19 MPa, and we've been given E for the material to be 202 gigapascals. So all that we have to do is just substitute the known variables into the equation to calculate the strain, and we get a value of 5.045 times 10 to the power minus 5. And don't forget, this is dimensionless, so don't be any units. Okay, so if this is the case, and we've already expressed that the extension or the change in length delta L will be equal to the product of the original length and the strain, then all that we have to do is just substitute known values, do the multiplication, and we get the extension in section 1 to be 4.0356, or if you want to do it 4.04, feel free to do so, times 10 to the power minus 3 millimeters. We do likewise for section 2. So again, calculating the extension in section 2, so the change in length in section 2 will be equal to the strain in section 2 times the original length of section 2. So since strain is equal to sigma divided by A, we've calculated the stress for this particular section, so that was 48.51, and we know what the Young's modulus is for the material, which is 202 times 10 to the power of 9, or 202 GPa. We do the multiplication and the computation, and we get 2.4015 times 10 to the power minus 4, and it kind of makes sense, okay, because the cross-sectional profile is smaller to that of section 1. Thus, the measure of strain will be greater. So now that we've calculated what the strain is, we can then proceed to calculate the extension experienced in the bar, this part of the bar. So delta L2 is equal to the product of epsilon 2 times L2. Okay, so don't forget that epsilon characterizes the strain and L2 characterizes the original span of the component. So the product of the strain and the original length will yield 1.441 or 1.4409 times 10 to the power of -2 millimeters. So now that we know the extension in section 1 and we know the extension in section 2, all we just have to do in terms of the total extension experienced by the bar is to work out the sum. So the total extension in the bar will be equal to the extension in section 1 plus the extension in section 2. If we do the sum, we get a value of 0.0185 millimeters. And there we have it.
This. The last part is to calculate what I believe would be the factor of safety. So we've now covered the factor of safety. So this makes it very easy for us to understand how we need to go about doing this. So to calculate the safety factor, so the safety factor, the factor of safety, however you want to call it. So that would be S subscript F. Again, you can use small n if you want. So that would be sigma y divided by sigma or whatever the working stress is. Okay, so let's call this 7. In the problem, we've been given sigma y to be at 205 MPa. So for section 1, the safety factor is equal to 205 divided by 10.19, and for section 2, the safety factor with respect to section 2 will be equal to 205 divided by 48.52. The bases are both in MPa, so MPa counts as MPa to leave the safety factor dimensionless. 205 divided by 10.19, that gives, let's write that as 20.12, and 205 divided by 48.52, that gives, let's say, 4.23. And I think it makes sense because if we look at section 2, it's got very little material to resist deformation against applied force. And secondly, that was the section that experienced the greatest strain. So it kind of like makes sense that the factor of safety will be smaller compared to the solid section of the step bar. So it kind of like makes sense. So we're told to calculate the average. So safety factor average will be equal to the safety factor of section 1 plus the safety factor of section 2, all divided by 2. Okay, so this will translate as the sum. So let's call that of the safety factor I over n. Okay, so we're going to kind of like write this mathematically. So that's essentially what it is. So if we're looking at a component with 4, 5, 6 distinct sectional profiles, we want to work out the average, then we can use this relationship to do so. So this gives us 20.12 plus 4.32 all divided by 2. 20.12 plus 4.23 divided by 2, and that gives an average of 12.18. And that's how we work through question 1.
So the next part is to calculate the safety factor experienced in each section. If we're assuming that this time the materials changed, if the materials change and we're using some material that has a slightly higher Young's modulus, okay, so we're probably looking at a higher quality steel. So we shouldn't forget that in this context, okay, the stress devoid of the material will always be the same, because the stress is a function of what? The cross-sectional profile to the applied force. So the stress that we've calculated will not be compromised if we keep varying the Young's modulus. What's going to be affected is the strain. So we're looking at the safety factor, and hopefully you've watched the video relating to the factor of safety. So the factor of safety will be equal to the stress limit divided by the working stress. So the stress limit has been given as 205, okay? So 205 MPa, which was more or less given in the problem. And we're dividing that by the stress in section 1. And if we do the division, we get 20.12. Okay. So since, as I stated in this particular lesson, that the safety factor ideally should be greater, okay, than 1. That is greater than 1, so therefore we are certain that the applied load of 20 newtons will not cause the component to deform plastically. And we're hoping it's likewise for the hollow section. So we do likewise for section 2. So the fail limit, 205 MPa, divided by the predicted stress of 48.51 MPa. That gives a safety factor of 4.23. So the good news is the safety factor is greater than 1. Thus, when the load is taken off, there won't be any plastic deformation. But again, it's subject to the amount of time that the material is enduring that particular force. However, when we compare the value of the safety factor in section 1 to the safety factor in section 2, you notice that because the safety factor in section 2 is considerably smaller than the safety factor in section 1, if there's any tendency of permanent deformation based on the time duration that the force is going to be applied to the component, then the likelihood of failure will be in section 2. But based on the values that we have, it's more or less improbable, unless there are microscopic defects in the material which will cause an increase of localized stresses within that region. So to work out the average, that will be the sum of the safety factor in section 2 and section 1 divided by 2, and that gives an average of 12.2. And again, the safety factor is dimensionless. And there we have it.
Alright folks, so hopefully everything makes sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.